Welcome. In the previous two sessions, we found how to calculate the derivative at a specific number. But if that's all we can do, it's not very useful because we're basically using the general idea from the ground up all the time. It's not very efficient. There are more efficient ways of calculating the derivative. The first step in that is to think of the derivative as a new function. In a sense, that's where the name comes from. We derive a new function from the given function by taking rates of change or slopes of tangent. So if I have a function f, I construct a new function whose domain consists of all the numbers at which the original function f is differentiable, and any such number c where f is differentiable, we define f prime of c to be value of the derivative at c. This explains the notation we used for the derivative with the f prime with c within parentheses, which makes it look like a function. That's because the idea really comes from here. So f prime of c, recall, is defined either as the limit as x approaches c of the difference quotient f of x minus f of c over x minus c, or the limit of the difference quotient written in the form f of c plus h minus f of c over h, with h approaching 0. Okay. If you want to find f prime as a function, we would like to use x as the variable. So in the second definition, we can just change c to x. In the first, we have to be more careful since there is also another variable in there. In this case, we might write f of t minus f of x over t minus x, and then take the limit as t approaches x. And the second one, this is easy to write, but somewhat longer to calculate. Here, it takes more time to simplify the difference quotient, but finding the limit will be immediate. It's customary to use this, and that's what I will do. But we have done a couple of examples before where we use this approach, and I will refer to that at the appropriate time. We will start by finding the derivative using the definition for some simple functions. Let's first find functions where we know what the slope is. Simplest function is a constant function. A constant function doesn't change. Its graph is a horizontal line, so the slope is 0. Rate of change is 0 because there is no change. So we know the answer should be 0. We are going to verify that. So if I take any number x, then f of x plus h is a constant k, so is f of x. So the difference in the function is k minus k, and that's 0. 0 divided by h is 0. Remember, h is not at 0. We haven't done the limit yet. Now that we have simplified the difference quotient, we can find the limit. Of course, since we have a constant, the limit is the constant, 0. The next simpler type of function are linear functions. And the simplest non-constant linear function is f of x equals x. But for any linear function, we should get the answer to be the slope. And for any linear function, it will work the same way this example does, an extra step in the algebra, but not much more complicated. So we take the function f of x equals x. F of x plus h is x plus h. F of x is x. So difference quotient is x plus h minus x. We have to divide it by h and then take the limit as h goes to 0. If I simplify the difference quotient, the numerator is x plus h minus x, or just h. So difference quotient is h over h, which is 1. And since there's a constant, the limit equals the constant 1. So again, we get the expected answer. Now let's up the ante a little bit. Let's take a function which doesn't have a constant slope, a nonlinear function. The simplest nonlinear function is x squared. So what happens if I do this with x squared. By now, the drill is clear. Find the difference quotient, simplify, take the limit as h goes to 0. If f of x is x squared, f of x plus h is x plus h quantity squared minus f of x, that's x squared, that whole thing divided by h. Now I need to simplify this, so I need to expand x plus h quantity squared. That's just a square of a binomial, and you can either FOIL x plus h times x plus h or use the formula for square of a binomial. Either way, you will get x squared plus 2xh plus h squared. And then I have minus x squared for the numerator. The like terms are x squared and minus x squared. They cancel, so I just have 2xh plus h squared in the numerator. I can factor out an h, which gives me h times 2x plus h in the numerator. Now we can reduce, because we can cancel the common factor h. So the difference quotient simplifies to just 2x plus h. And since it's a polynomial in h, the limit equals the value. As h goes to 0, we will get 2x plus 0 or just 2x. So derivative of x squared is 2x. Let's step outside the realm of polynomials to rational functions. The simplest rational function that's not a polynomial is 1 over x. Let's do its derivative. If f of x is 1 over x, f of x plus h is 1 over x plus h. F of x is 1 over x. I have a complex fraction. Just for variety, I'm going to simplify this the less usual way. We will simplify the numerator, write it as a single fraction, then divide by the denominator. The common denominator for x plus h and x, or 1 over x plus h and 1 over x, is x times x plus h. So I'm going to write both fractions in the numerator, the two little fractions in terms of that. In the first fraction, the extra factor in the denominator is x, so I need to multiply the numerator by x. In the second fraction, I need to multiply the numerator by x plus h. And now I can combine the two little fractions in the numerator. So I get x minus the quantity x plus h divided by x times x plus h. Don't forget to distribute the minus, which gives the numerator as x minus h divided by x times x plus h. Now I need to divide this. This quantity is just the numerator here. I need to divide it by the denominator h, which I'm going to think of as the fraction h over 1. To divide by a fraction, I take the reciprocal and multiply. So I multiply this fraction by 1 over h, and while we're at it, let's combine the like terms here. So that gives me x minus x is 0, so I just get negative h over x times x plus h, which I need to multiply by 1 over h. I can reduce this by cancelling the h's. I get negative 1 over x times x plus h. This is not a polynomial, but as h goes to 0, the denominator approaches x times x plus 0 or x squared. So the limit will exist as long as x squared is not 0. Remember that our original function was 1 over x, which is defined only if x is non-zero. So if x is non-zero, so that the function is defined, then this limit will exist and be equal to negative 1 over x squared. So that tells me that the derivative of the function 1 over x is negative 1 over x squared. Of course, we can continue like this, trying to find derivatives of specific functions and make a big list, but we are going to try to make this even more efficient by coming up with some scheme for writing down the expression for the derivative, writing down an expression for the derivative, given an expression for the original function. This is the task ahead of us, which we'll come to next time. Goodbye for now.